Let's begin section 4.1, the formal definition of the derivative. This section really gets to the heart of Calculus 1. Now, I do want to make a couple of changes. Even though we're going to talk about time, I think it's helpful to talk about it in terms of the letter x, just because we're used to dealing with x's and y's. Let's get rid of this guy. I'm going to call this guy f of x equals x squared plus 7x minus 6. And we have a population consisting of this many people at time x, and we're interested in the rate of change of the population at time x equals 3. The instantaneous rate of change. How quickly is this population increasing? Okay. Now, I also asked the question, what is the slope of the tangent line to y, or I should say y equals f of x equals x squared plus 7x minus 6 at x equals 3. Now, if you remember, I asked this on one of the first days of class. And if you remember, I said these questions, while they look completely different, are actually the same thing. And I told you the answer to the questions, and they probably didn't make any sense at the time. So we're going to see what the answer is and why it does make sense right now. So consider problem 1, and suppose that we graph this curve, right? So we have something like this. X-axis, y-axis. I don't think the parabola is super nice, but it's something like this. And suppose right here is x equals 3. Right, we've got that. Of course, we have this value, f of 3. Well, which we can actually see what that is, right? Well, I'll keep f of 3. But just to point out, we could plug 3 into f, and we get 3 squared is 9. So I think we're getting 24, right? I think we're getting this equals 24, right? I just plugged in 3 into this function, right? 3 squared is 9, plus 7 times 3 is 21, minus 6 is 24, okay? So anyway, this is the graph y equals f of x. And we want to find the instantaneous rate of change of this curve. Well, what do we mean by that? Well, let's think about this for a second. Well, we have we have this notion of rate. If we think back to middle school, I remember learning this in 6th grade. We have that rate equals distance over time. Now I'm going to be technical and call it displacement over time. The only reason I'm calling it displacement and not distance is because distance is always non-negative, whereas displacement could be negative. If we go backwards, then we have negative displacement. Okay? So why do I write this? Well, if we consider just some kind of a line, maybe in some value, we'll call this just x. Right? We consider one point, we'll call this guy, actually I'll call this x1. And so this right here has x1, comma, y1. And then this point right here is, well, I guess it's, I guess I could call this guy 3 and f of 3, which we know is 24, right? Well, I guess we could say that, okay, the slope of this line right here, is that really a straight line? Yeah, so that's a straight line. The slope of that line, well, actually, I'll just write it as slope. Remember that equals y2 minus y1 over x2 minus x1, right? We should remember that. Well, in this case, it's going to be f of 3. Or I should say, actually, I guess I should call this, yeah. So I guess that is, right? It's f of 3 minus f of x all over 3 minus x, right? Or I guess I should say, sorry, let me actually, instead of calling this x1, y1, I'll call this x1, f of x1. Okay. Right, so I just did this y value minus that y value over this x value minus that x value. Right? And I suppose we could write this the other way too, right? We could write this as f of x1 minus f of 3 all over x1 minus 3. Okay? But we could say, well, how does this help? This isn't the instantaneous rate of change. No, this is the average rate of change. Okay? Right? This right here is average rate of change. And it equals this too. But what we could do is we could say, well, okay, hold on a second. x1 was not a very good approximation. Let's consider this value on the line, right? And do the same sort of thing, right? And eventually we could make this as close as we wanted to our curve, right? We could get real nitty-gritty. Let's see if I can straighten this line. Maybe we get right over here, right? And we can make this point arbitrarily close to our point, right? I'm just going to call this guy x, right? And so we have that, let me fill that in a little bit more, that the slope becomes f of x minus f of 3 all over x minus 3. Right? And this is just coming from the fact that this right here, this is the x value. This is f of x. And so we have the slope of this secant line. Now, we're not really interested in the slope of this, what we call a secant line, because we're not interested in the average rate of change. We're interested in the instantaneous rate of change. So it turns out that the instantaneous rate of change equals the limit of this. The limit as x approaches 3 of f of x minus f of 3 all over x minus 3. You see how we found the instantaneous rate of change by considering the average rate of change and then taking the limit of it, making x get arbitrarily close to 3 and finding the slope of that line. Well, if we take that limit, then we actually have something else. We have the slope of what's called the tangent line. In fact, let me use another color to make that pop. Okay. And this equals the slope of the tangent line. Okay. Now, another way to write this is to write this as the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And this is by letting, let x equal 3 plus h. I'll get more into this in a sec, but just want to point out that if we go to the very first set of notes where we do this stuff, where do we have this? I told you what the answer was, and sure enough, these were the answers. Okay? So that's where I was getting them from. Okay? Now, what are we really doing? We're just trying to find a limit, right? We're just trying to find, well, I guess I'll just put it down here. This guy. And I will just point out that this equals this guy. Okay? So let's do it. Now, first let's have a couple of different, let's just introduce a couple of pieces of terminology here. Given a curve y equals f of x and a point, we say that the line tangent to y equals f of x at x equals a is the line through the point a comma f of a with slope, that's going to be the limit, as x approaches a of f of x minus f of a all over x minus a. Okay, now it touches the graph at exactly the one point a comma f of a. So really problem 1 and problem 2 actually, they're asking us to find the slope of the tangent line to this curve. Oops, sorry, this is actually not the right curve. It's supposed to be this. X squared plus 7x minus 6 at the point 3 comma 24. Okay. Now this is what I had before, letting x equal 3 plus h, which is to say, consider h going to 0. We have that the instantaneous, I wrote this down, but I'll write it again. The instantaneous rate of change equals the limit as x approaches a of f of x minus f of a all over x minus a, and that also equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So we're often going to use this kind of notation. So we define the derivative of f at a to be the function f prime such that f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay? So just to point out one more time, f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. And that also equals this other limit, which we're not going to use quite as often, right? That x approaches a of f of x minus f of a all over x minus a. Okay. So anyway, given this population function, again, I'm just going to call it x. It doesn't really matter, but just call it x because I think we're used to x's. All right, find the instantaneous rate of change at time x equals 3. Well, what are we going to do here? We're going to say f prime of 3 equals the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Now, you can just plug in h equals 0, and you'll see that we're going to get 0 over 0. It's going to work this way every single time, just by definition, so you don't need to do it. But we're going to take this limit, and we're going to take it in by just using f of x, right? We know what f of x is. So instead of f of 3 plus h, we're going to get 3 plus h quantity squared plus 7 times 3 plus h minus 6. You see that this is this, which I just got from plugging into this guy. I plugged 3 plus h in. Right, and I'm just going to say minus, and then I'm just going to plug in 3 squared plus 7 times 3 minus 6 all over h. And you see that I got this from here, right? Just plugging in x equals 3. Right. So we can simplify this out. And we're going to get just a little bit of simplification here, right? Little bit. But we're okay. And then this whole thing right here is going to be 24. But let me actually just point out that this is the same as minus 9 plus 21 minus 6. All over h, okay? You see, I just did a ton of simplification. Right? This is just that. This is just that stuff in yellow. Okay. And one thing to notice is that the constants cancel out. Right? And that's not a coincidence. It should always work out that way. If it doesn't work out that way, you did something wrong. Okay? So anyway, we are left with the limit as h approaches 0 of... Looks like we have h squared plus 13h all over h. And of course, we know that if we take this limit at this point, we have 0 over 0. But I also hope we see that we can just factor the top and the bottom, right? H plus 13 over 1, right? And now we just get 13. 13 people per unit of time. And sure enough, I just want to point out that, look, we used our standard limit techniques, right? We just factored stuff. If we go to the first day, we did this stuff. I told you. Oh, man, I lied. I told you the answer was 13, right? And we just proved it. Get rid of that, right? Now, if you remember also, I kind of eyeballed it. So maybe there's a little more than meets the eye. Maybe I'm using some kind of a shortcut, but we don't know about that. So anyway, for right now, let's just consider an example, right? Object has position f of x equals x squared plus 3x times x. Write the expression for each of these guys. Well, number one, the average rate of change from times 4 to 7. I'll just write average rate of change equals f of 7 minus f of 4 all over 7 minus 4. We can do this out, right? We're going to get 7 squared plus 3 times 7 minus 4 squared plus 3 times 4 all over 3. Right? 7 minus 4 is 3. And what does this boil down to? What, 49 plus 21 is 60. Minus, was that 6, minus 28 all over 3. What is this? So 32 over 3, 32 thirds. Okay, well, the instantaneous rate of change is going to be the limit as h approaches 0 of f of 4 plus h minus f of 4 all, no, try that better, there, all over h. Okay, well, actually, the derivative at time 4 is, like for number 3, that's the same thing. And I guess the slope of the tangent line at 4, well, that's also the same thing. So I guess all of these guys are really the same thing. So this is just to show you that for 2, 3, and 4, I could ask you to find the derivative of a function in a million different ways. Okay? Let's actually do it. F prime of 4, right? Let's answer questions 2, 3, and 4. Right? We answered question 1. Let's do 2, 3, and 4. Well, it's going to be this guy, right? I'm just going to copy, paste, or duplicate, right? Well, again, we know what f is. We know that this is really the limit as h approaches 0 of 4 plus h squared plus 3 times 4 plus h minus f of 4, which is going to be 4 squared plus 3 times 4. And then this is all over h. Right? And at this point, we just simplify a bunch, right? We're going to get 16 plus 8h plus h squared. And we move that down a little more. And then this is going to be minus, we said that was 28. Oh, wait, hold on a sec. Sorry, I lied. I forgot the second term here. Plus 12 plus 3h, and now it's minus 28. This is all over h. Right, just to point out where I'm getting this from. This part is this. I just foiled it out. this part becomes this. I just multiply it out, and then this part right here is this. Just multiply it out, okay? And one thing to note is, sure enough, the 28 cancels with the 12 and the 16. Again, it always works that way. It's very nice. So anyway, we're left with the limit as h approaches 0 of h squared plus 11h all over h. And of course, this gives us 0 over 0. So we just factor stuff out, and we get limit as h approaches 0 of h plus 11, which equals 11. And that's our answer.